Okay, so today we're going to be going over EE370 in order to prep for the final. And so we're going to start where we left off, which was on root locus. So what is root locus? Basically, the root locus is the path of closed loop poles as K is changing. So we're going to look at this and get into this a little deeper, but just know it's a path that we're going to be trying to make. And so that's what we're going to be looking at in the very beginning. And so a lot of times what we see is we have a complex number, which is in the S plane. It's given by S is equal to sigma plus J omega. And so then the real part of this complex number, so the real part of S is going to be sigma, where the imaginary part of S is going to be J omega. What we're going to see, just the omega part, because remember the imaginary part is the J. So the imaginary part of S is just the omega term right here. And so what we see is when we graph this on the S plane, what it looks like in particular is within our S plane, we have the sigma on the real axis and we have the J omega on the imaginary axis. And so what we can tell is this can be represented as well when you have vectors specifically. A vector, or as we like to call them, phasors, how they start from the origin, they have a magnitude and they're going to have a phase angle. So the magnitude would be the length of the vector and the phase angle would be from the real axis up to the phasor that you have. And so what we're going to notice here is that in order to calculate the magnitude of this complex number S here, your magnitude of S, which I'm going to represent with the absolute value bars, is going to be the square root of sigma squared plus omega squared. And then for your phase angle, it's going to be the tangent inverse of, and then your imaginary part is the omega over the real part, which is the sigma. And so this is given with your magnitude and phase angle, and that would be in a polar coordinate because it has a magnitude and the phase angle. But if you want to go from the polar form, which is the m with a phase angle of theta, to the Cartesian form, in the Cartesian form would be what's along your real and what's along your imaginary. In order to find how much along the real part, it would be m cosine of theta. So how much is along like this x-axis, where your imaginary part, which is the omega, is going to be m sine of theta. Okay. And so to convert between the two, this is how you would go to polar, get your magnitude and phase angle from the Cartesian elements here, the sigma and the omega, and how you would go to Cartesian from the polar elements of the magnitude and phase angle. And so now that we see that, what we're going to notice a little later on, what happens is we deal with complex functions. And so a complex function, what is it? And we'll see why this is important in order to apply our phasor knowledge. A complex function is basically a function whose, and then this would be input or argument. So you can say argument, same thing as the input, is a complex number. And it outputs or generates, same thing, another complex number. So it takes in a complex number and it generates a complex number. And so what we like to do is in mathematical notation, we just say a function. It takes in a complex number, so the C for the complex numbers, and it's going to generate. And so that arrow represents generating another complex number. And so what we're going to do is have an example. And for this example here, we're going to have a complex function f of s. Notice that s's are complex because it has a real part and imaginary part. And so this is a complex function because it's a function of s, and it's defined as s plus 1 all over s times s plus 2. And so what is, and then f of s1, if s1 equals, and then -3 plus j4. And so what we see here is our S1, we're going to plug that into our function. Our function's defined here, f of s. And so we're going to plug in for s, the value of S1, which is right here, -3 plus j4. We can tell off the bat this is a complex number. It has a real part and an imaginary part. And so what we're going to see here is what's going to happen basically is if we show this in our Cartesian format here, this is -3 plus j4. So if we go out 3, so this would be our -3 point, and then we go up by 4, so that's around here. This is what we would be used to seeing for S1. It is -3 along the real axis, and it's 4 units up on the imaginary axis. And so that's what we're used to. But for this one, what we're going to notice is our complex function here. Don't you notice that there is a 0 defined at s equals -1? Because when you have s plus 1 set it equal to 0, you're going to then get s is equal to -1. So we're going to plot that here. So we have a 0 at -1. So here at -1, we have a 0, and that's just because of our complex function. Then we're going to notice we have poles. We have a pole at s equals 0. And then we have another pole at s equals -2. Okay. So now that we have all those, we're going to connect these ones to our point here for S1. And so what we're going to do is we're going to draw 3 arrows. And it starts from these poles or zeros from our complex function and goes up to that point S1. Okay. So you'll notice we have 3 lines now. And what we're going to do is I'm going to give this first one from the pole at 0 up to our S1 point. I'm going to call this M1 and then give it the angle of theta 1. And then here for my second line here at the 0, -1, I'm going to call this one M2 with an angle of theta 2. And then the third one here is going to be my M3 angle 3. Okay, so I just labeled all 3 of those. And what we're going to notice is basically, if we're trying to evaluate this, you're going to get for your new magnitude from running this number through this complex function, we're seeing the contribution by both the poles and the 0 upon creating the new magnitude and the new phase angle for the new phasor that this is going to generate at its output. Because remember, it takes in a complex function, which it's taking in this one here. It's going to generate a new complex function. So it's going to generate a new phasor. So we had the original phasor up to S1, and we're going to generate a new one of f of S1. And so from this point, what we're going to notice is recall. The zeros are always in our numerator. So we're going to have the magnitude of our 0 in the numerator. And then remember, the poles are always in the denominator. So we're going to have the magnitude of the poles in the denominator here, M1 and M3. And then we're going to get a new phase angle because we're getting f of S1. We're getting a new complex number. So that will have a phase. And what is our phase going to be? Remember that the phase angle of the 0 is in the numerator, so our theta 2, but the phase angle of the poles are in the denominator of your function. So that's why it's minus, and then it's going to be theta 1 minus theta 3, because these are from our poles, where the theta 2's from our 0. So now that we got that, when you plot then the new magnitude and phase angle, you're going to notice when you specifically do that calculation, you're going to see that f of s1, which would be the new phase phasor, sorry, it's going to have magnitude n, and then it's going to have a phase angle, and then here we just defined it as phi. And so this would be our f of s1, the new complex function that was generated as a result. And so that would be showing it graphically. If you input a complex number into here, so that complex number was -3 plus j4, and then we use what we had to find here for our complex function. We graphed the 0 and we graphed the 2 poles, then we connected it in order to find out the magnitude and the phase angle contribution by each, in order to determine what's going to be the complex number output by this complex function. So what's that phasor's magnitude and phase angle going to be? And that will generate our capital F of S1 for output. Okay, now that we talked about that, in order to determine, we're going to look at the unity feedback system. So if we have a unity feedback system, that's going to be given by an input R of S, and then it's going to run through specifically here. We're going to see this would be plus, and then here minus. We're going to have our controller, which is our K, that determines the amount of gain we're going to see. And then we're going to have our plant, which is our system, so G of S. And then it's going to be at the output stage, Y of S. And what we're going to notice here is, what is the open loop system? So the open loop system, it would no longer be closed. So think of looking at this, just going in this direction here. So for your open loop system, you're going to see that it's just K times G of S. That is your open loop system. So we're going to call that L, in which L of S is going to equal K times G of S. Just what's in here, K multiplied by G of S. And we're going to see that G of S, remember, that's our system. So it's going to have a numerator, N of S, all over the denominator, D of S. And so the N of S would just be your zeros within this system, and then D of S would be your poles within that system. And for our closed loop system, now we have that feedback, which closes the loop. And so for that closed loop system, we're going to notice that T of S is going to equal, and then it's going to be what's in your, what's your open loop gain, which is Kg of S, all over 1 plus, and then our feedback is unity, so it's just Kg of S. And then we're going to notice when you write G of S in terms of N of S over D of S, here, if you substitute that in, you're going to get Kn of S all over, and then you'd have your D of S plus Kn of S. And so that's what we're going to see for a closed loop system. When you just substitute in for G of S, N of S over D of S, and multiply everything by D of S, you're going to get that result. So what about your open loop zeros? For your open loop zeros, what you're going to notice, that's when N of S will equal 0. For your open loop poles, you're going to notice that's when your denominator is going to be equal to 0. So that's when D of S is equal to 0. And then now when we're looking at our closed loop zeros, you're going to notice the closed loop zeros are going to occur when our numerator here is equal to 0. So that's going to be when your n of s, because remember, k is just a constant, but your n of s actually has the location of your zeros. So it's just when n of s equals 0. And then your closed loop poles, you're going to see that's when your denominator here, d of s plus k n of s, is going to equal 0. And so now that we've seen that, basically, what we're going to have to determine is when is this system stable? So when is the system stable? And so what we oftentimes see when we deal with our closed loop systems, that's when we're interested in our stability for a closed loop system. And so what we notice for the closed loop system is our T of S is equal to K of G all over 1 plus K of G. And so you're going to notice, remember, it is going to be stable when we're looking at the denominator here, making sure that's like not a divide by 0. So we don't want any of our poles to be in the right-hand plane. And so what we're going to have here, in order to determine stability, is 1 plus k of g is going to equal 0. From the denominator, we set that equal to 0. And so let's do an example for a unity feedback system to see how this comes into play, because here's a lot of definitions. And you have to distinct these two, because this deals all with the open loop system, which we see here is when we don't have the feedback. But once you introduce that feedback element, that's when you close the loop. And then that's why we have different values. We'll see for closed loop poles versus open loop poles. So you have to be careful when you're dealing with a certain type of system. And we're interested in closed loop systems because they provide stability. And so that's why we oftentimes look at our transfer function, the closed loop system, the denominator here we set equal to 0. So for an example here, we're going to have a unity feedback system. So we'll have an input to this unity feedback system, and then it's going to go through a gain factor k. And then we're going to have 1 over s times s plus 2. And then we're going to have our output c of s. And so what's going to happen here is, what are the open loop poles? Okay, so we have to find our open loop poles. Remember, our open loop system, which is just k times 1 over s times s plus 2, our poles are going to be what's in the denominator here. So when we have our actual system, L of s, which is equal just to k times g of s, which we rewrite as k, and then what's in the numerator here, it's going to be 1 all over and then s times s plus 2. So for poles, that's what's in the denominator. So our open loop poles, if we solve for that, that would then be s times s plus 2 is equal to 0. You're going to get s is equal to 2 and s is equal to -2 when you solve for s, because the poles refer to what's in the denominator of g of s. So that's why we were interested in setting s times s plus 2 equal to 0. Now, when it asks for you for your open loop zeros, notice that within our open loop system, L of s, that there's no s terms in the numerator here. So we're going to have no zeros. Okay. Now that we talked about the open loop poles, the open loop zeros, we need to look at the closed loop poles. So for closed loop poles, what we're going to be looking at is when we actually close the loop, what is our transfer function given by? And so we're going to determine that if you close the loop, it's going to be k times g of s, where the g of s here is 1 over s times s plus 2, all over 1 plus k g of s, 1 over s times s plus 2. Now you're going to get k all over, and then s times s plus 2 plus k. And so that's going to be your transfer function. And so for poles, remember that refers to the denominator here. And so our closed loop poles, we're going to have to look at this denominator value. So when s squared plus 2s plus k is going to equal 0. And that's going to occur. What we're going to see here is when we have different values of k, that's going to change where closed loop poles occur. Because when you solve for this, you're going to notice when k equals 0 versus k equals 1 versus k equals 2, where are those poles going to be located? And so when k equals 0, in this denominator, it's just going to be s squared plus 2s is equal to 0, where that's just going to be s times s plus 2 would equal 0. So your poles would be at s equals 2 and s equals -2. Okay, when k equals 1 here, you're going to get s squared plus 2s plus 1 is going to equal 0. And so what we're going to notice is your s, there's going to be a double pole at -1, because this is just s plus 1 squared, where so each of the poles is at -1. You have 2 poles at -1. And then when k is equal to 2, you're going to have s squared plus 2s plus 2 equal to 0. Here we're going to see that when you solve it using the quadratic equation, you're going to get -1 plus minus j. Okay, so if we graph this, what you're going to see here is an interesting discovery. You're going to start out right here for this initial condition. So I'm going to do these in different colors so you'll notice. For the k equals 0 here, you're going to have a pole at 0, -2. So one at -2 and one at 0. And then when your k equals 1, you're going to have 2 poles specifically at -1 here. So that's a double pole at -1. And then when your k equals 2, you're going to see that your poles are going to move upwards. One's going to be at -1 plus j, one's going to be at -1 minus j. And so notice that the value of k, when it increases here, our poles, they started out at 0, -2. So we started at -2, and then it went upwards, and then we're going to have here from 0, and it's going to go down to -infinity. So what you're going to notice is that once you increase the value of k, the closed loop poles basically are going to follow along this path. And so they're going to go up to positive and negative infinity. And so what are the closed loop zeros here? Notice that we don't have any closed loop zeros because there's no value of s in the numerator. So for a closed loop zeros, there are no zeros because there's no s terms in our numerator for that closed loop system. And so now that we saw that, what we're going to notice later on is that basically, when we increase our k, notice that the path of the closed loop, it goes up to infinity, negative infinity. But the biggest thing is there's 2 paths, one that goes up to positive infinity, and the other that goes to negative infinity. And notice that we have 2 poles. At each of these k's, we had 2 poles, 2 poles, and 2 poles. And so you'll notice with the root locus, based on the number of poles you have, that's going to determine the number of paths you have in your root locus. And so now that we talked about that, we're going to get back into what is our root locus. Our root locus is going to be the path of these closed loop poles as our gain k is varied. And so now that we talked about that, we're going to now look at the rules to the root locus. So these are very important in order to follow. So we're going to look at each example. So when we start out basically with our unity feedback system, the very first thing when we're looking at the root locus is you want to write the characteristic equation such that the parameter of interest, which remember, when we're dealing with root locus, it's the value of k, which is the gain, appears as a multiplier. Okay, so for this, you're going to see the equation 1 plus k L of s is equal to 0. And remember, L of s refers to your open loop system. What we're going to see with this is your root locus specifically is going to deal with. Remember, we were so interested in the unity feedback system because within this unity feedback system here, we had the parameter k, which is our gain, and it goes through g of s, which is our plant. And then this is produced to the output, which is c of s, but it was connected here and there was feedback. But we said that, remember when you make your t of s here, it was k g of s all over 1 plus k g of s is equal to, and so when we look at the poles, remember, we're interested in the stability of the system. And remember, when we're interested in stability, it was of a closed loop system. You always look at the poles of that closed loop system. So here, isn't our g of s, because this is a unity feedback, remember how we said our open loop gain, it would be k times g of s. Well, here, your g of s, it is the exact same thing as the L of s here, because your open loop gain, you can think about it. And so that's why they say 1 plus k L of s is equal to 0. When you're working with unity feedback systems, you can call L of s g of s here. And so that's why you can write it as this characteristic equation up here. 1 plus k L of s is equal to 0, because we know from our closed loop system with unity feedback, you can write it in this format, and the poles are determined by the denominator in order to find the stability. And so here, because remember, your open loop gain follows the exact same thing where it's k times g of s. And so instead of g of s, remember your open loop system deals with L of s. So we just substituted it in for g of s, L of s. And it's the exact same thing because it's unity feedback. Okay. Then your next step would be that you want to factor L of s in terms of n poles and m zeros. And what do I mean by this? So when you have to determine the root locus, you're going to see basically that from this characteristic equation that we have, we're going to write it actually in terms of our poles and zeros. So remember, zeros are in the numerator, and then dot, 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 it's all multiplied by, and then s plus z of m, because the total amount of zeros that you have all over the total amount of poles you have. So s plus p 1, and then multiplied by, and then all the way up to s plus p of n. And that's going to be equal 0. Notice that's the exact same thing as my characteristic equation here. I just substituted in for L of s the zeros over the poles. And so that's what we have here. Exact same thing, just substituting in for L of s. And so after we do that, then you locate the open loop poles of L of s in the S-plane. And so in order to determine the open loop poles of L of s in the S-plane, you're going to when you graph it, you use an X for poles, and you're going to use the circle for zeros. Okay. Now that we talked about that, that's sort of like the preliminary stuff to the steps that we're going to be taken whenever we have to define our rules for the root locus. So this is sort of all preliminary work that we had here. Make sure that you have it written in terms of a unity feedback system. So you can make sure that you have the characteristic equation here. And so then after you get the characteristic equation, make sure you know where your zeros and poles are, rewrite it so that you can write your zeros in the numerator all over your poles. And so then you're going to plot them. And from that plot, so all this, I want to say, is sort of your pre-work to all the rules here. So this is sort of your preliminary analysis. You want to make sure that you get that unity feedback. And then after you get the unity feedback system, you make sure you write it in terms of this characteristic equation. You substitute in your zeros over your poles. Now we follow the rules of the root locus. So the rules are very defined. And so we're going to go one by one. So for a root locus, rule number 1 is that the number of paths is going to equal the number of closed loop poles. Okay. And so what we're going to see, let me do one more rule, and then we're going to look at examples. The second one is that the root locus must have symmetry with respect to the real axis. Okay. So now that we've seen that, let's look at a visual to get a good cue behind these two rules here. And so for our visual example, remember, we're dealing with the S-plane, so we have sigma on the real axis and we have j omega on the imaginary axis. And so we're going to say that our poles were at -1 here, -2, and then we have a 0 at -3, then we have another 0 at -4. And what's going to happen is we're going to see that there are 2 closed loop poles, correct? So we can have only 2 paths. So that's from rule number 1. We have 2 closed loop poles. So we're going to have 2 paths for a root locus to take. The next one is that our root locus must be symmetrical with respect to the real axis. And so we're going to see that it should be the mirror image when we flip it over. And so when I'm looking at this, I notice I have my poles here, and then it's going to go over. So the first one, what we're going to notice is it's going to go into here, and then it's going to go to one of the zeros, where the other one's going to go, it's symmetrical, so it goes exactly the opposite way, and then it's going to go to the other 0 here. And so what we're going to see is that with our path, there were 2 closed loop poles, and one path went upwards where the other went downwards, but they were symmetrical with respect to one another. When you flip-flop it, it's symmetrical. So when you flip this side over this side, you'll get the other path. And so that verifies the 2 rules that we have so far of the root locus. Now that we have that, our third rule is that basically, when we're working with the root locus, we're dealing with k as it goes from 0 to infinity. So that's what we work with, k from 0 to infinity. So when we say rule number 3, it's going to be for k greater than 0, which is what we're interested in. The root locus, which is the path by the closed loop poles. So the root locus exists to the left of an odd number of real axis open loop poles and or zeros. Okay, so what does this mean for an example? So let's look at an example here. So we're going to have our real axis. And so sigma, our real axis, then remember j omega is our imaginary axis, because we're working in the S-plane for the root locus. And we're going to have j1 here, and we're going to have negative j1. And we're going to have two poles, which are at -1 and -2, and we're going to have two zeros at -3 and -4. Okay, so what we're going to notice is our root locus exists to the left of an odd number of real axis open loop poles and or zeros. So when I go from the right-hand side, I'm starting at the very rightmost point and I'm searching. Is there a pole or a zero as I move to the left? And I'm going to count each. So, oh, I ran into my first pole. So I'm going to just have a 1 here. This is an odd number. Then I run into my next pole. Okay, this is 2. I run into my next 0. This is 3. Then I run into my next 0. This is 4. And so I just went from the rightmost side, and as I traveled to the left, if I picked up a 0 or a pole, then I would mark a number. So, and I would just increase that count. So I found 1, 2, 3, 4. So I found 4 0/poles. And so now that I have that, remember, the root locus can only exist to the left of an odd number. So what we see here is, remember, so it can go from the closed loop poles and it's going to go to our zeros. It's going to go, sorry, from our poles to our zeros here. And in this direction, remember, it's symmetrical. So we have the symmetry here. And with that symmetry, remember that that path broke out specifically. It was only there between to the left of this odd number pole where it broke out from the real axis, and where it broke back into the real axis, it was to the left of an odd number. And so the odd number 0 here was 3. So notice that to the left of an odd number, it's going to break out and break back into the real axis. So it doesn't break out or break into to the left of an even number pole or 0. So be careful, make sure it breaks out of an odd number pole or 0. Okay, now that we talked about that one, we're going to look at the starting and ending points. So this is the next rule that we're going to be interested in, rule number 4. And so the direction of the root locus direction of root locus starts from open loop poles and goes to open loop zeros or infinity. And so this one's pretty easy to understand, because as we've seen before with our diagram, we start from the poles, which were at -1, -2. Notice the direction of the arrows. We started here, and then we went to the zeros through each of these paths here. And so that's what rule number 4 is trying to tell us. We start at poles and we go to zeros or infinity. Now that we know that one, our starting and end points, we're going to look at the behavior at infinity. So this one basically says, rule number 5 is basically, if we don't have a 0 that it touches, and we're going to infinity. So this other case, this is what rule number 5 looks at. The root locus approaches straight lines. So it becomes like a straight line as the asymptotes as the locus approaches infinity. And so what we need to look at here is within our root locus, basically, the asymptotes that it approaches as it goes to infinity, say there's not a 0, and that root locus path is going to go towards infinity. The asymptote of the root locus, what we're going to see here is it's going to be the summation from 1 up to how many poles you have, so negative P1. So it's going to be the sum of all the poles. So, and then the sum here, notice there's a minus sign, and then this is going to be of all the zeros that you have. And then it's going to be divided by n minus m. And what you're going to see is that this is going to be your open loop poles. And this is going to be your open loop zeros, the number of open loop poles, and this is the number of open loop zeros. Okay, now that we have that, we have asymptotes, but we have to determine at what angle do those asymptotes occur. And so the angle of your asymptotes is going to be given by 2r plus 1 times pi all over n minus m. And your r is going to be defined as 0, plus minus 1, plus minus 2. And then you stop once it starts to repeat. And then what we're going to do here is let's look at an example. And so through an example, I think this one's really good to understand rule number 5 here. Because it can be a little confusing, the notation here, but this equation is very important. Make sure that you have both of these in order to determine where your asymptotes occur and at what angle do those asymptotes occur. And so now that we talked about that, let's just have a sub-example in rule number 5. So our unity feedback system, we're going to have R of S. And we have the summing block. So our summing block here, we're going to have a plus here and a minus here. Then it's going to go through k multiplied by s plus 3 all over. And then here it's going to be s times s plus 1 times s plus 2 times s plus 4. Okay, that's great. Then we're going to have, after our system, our output C of s. And then it's going to connect back to complete the feedback. And so from here, notice that this is a unity feedback system. I can perfectly write this as 1 plus k L of s is equal to 0. And then I could substitute in for my L of s here. It would just be 1 plus k. And then notice my zeros here. It's given by, notice we have the k already here. The k is multiplied by the system. So it's just going to be my zeros, s plus 3 here. All over, and then what are my poles? S times s plus 1 times s plus 2, and then s plus 4. And then we can just plot these afterwards. And so when we go to plot these, what we're going to see is when you do the specific plots, you're going to get the following. So we have a pole at 0. We have a pole at -1. We have a pole at -2. We have a pole at -4. -4, -2, -1, 0. Okay, and we have a 0 at -3. Okay. So that's what we were able to determine just from the start when we looked at here. And this is our preliminary analysis. And then we did all the plotting. And now what we're going to do is we're going to have to determine our asymptotes and our angle of asymptotes, because notice there's only one pole here, sorry, 1, 0, but we have 4 poles. And so some of these are going to have to go to infinity because only one will end up at the 0 for our root locus path. The other ones are going to go to infinity. So only one of these poles is going to end up at this 0. All the others are going to go to infinity. And so what we're going to do here is notice that how many poles do we have and how many zeros? So our n is the number of open loop poles. So we have 1, 2, 3, 4. Our m is the number of open loop zeros, which is 1. Okay. Now that we have that, our sigma a, which is the asymptote, basically determining this value that we have where the asymptote is going to occur, all of them, it's going to be the summation here of our poles. And so the summation of our poles here, notice that we have a pole at 0. So our first one's going to be 0 here. And then our next one's going to be at -1. So we're going to have -1. Then we're going to have next one's at -2. And then next one's at -4. Okay, that makes sense. That's all of our poles. And then we subtract where our zeros occur. So minus, and then our 0 occurs at -3. All over, and then n minus m, which is going to be 4 minus 1. And so here, when we plug this in, we're going to get -1 minus 2, -3 minus 4, -7 plus 3. It's going to be -4. And then in our denominator, that's going to become 3. So all these asymptotes are going to be centered at -4/3. So let me make a little notation here. At -4/3, that's going to be the center of our asymptotes. Now that we have that, we have to determine the angle of our asymptotes. So the angle of the asymptotes, it's going to be, well, if we start out with our r is equal to 0, we're going to notice that plugging in 0, we're going to get pi over, and then that's 3. Pi over 3 when r equals 0. So notice that's our first angle. Our next angle is going to be, let's plug in r equals +1. So that would be 2 plus 1, which is 3. So 3 pi over, and then in this denominator, it's going to be 3. So that would be 3 pi over 3 is pi. So that's when r equals 1. And notice that our third angle for our asymptote, if we plug in r equals -1, we're going to get here, when it's -1, it would be then minus pi over 3. And so now that we did that, if you plug in r equals 2 or -2, it's going to repeat one of these values. So that's why we stop here. Because if you plug in r equals 2, you're going to notice that you're going to get 4 plus 1, which is 5 pi over 3, which 5 pi, let me see. Sorry, when you plug in 2, yeah, 4 plus 1, which is 5 pi over 3 here. You're going to notice that's going to start repeating itself. And that's what we don't want. And so, because that's the exact same thing as -pi over 3. 5 pi over 3 is just add 2 pi. So that's why we stop here with 3, because then it's going to start to repeat itself every 2 pi. And so notice that what's going to happen is when we draw this now, we're going to have an asymptote that goes positive pi over 3. So I'm going to draw one asymptote going out this way. So this one is going to be the asymptote with an angle. Angle 1, here, let's see. Yeah, asymptote of A1 is going to be pi over 3. That's going to be our angle here. And then our next one is going to be pi. And so then that one's going to go, our next asymptote is going to be somewhere along here. It's going to go angle of A2 is equal to pi because it's a full pi here, what we're going to notice. And then our angle of asymptote 3 is going to be negative pi over 3. So here it's going to be negative pi over 3. For the asymptote angle A3 is negative pi over 3. So there's our asymptotes, which is really good. Now we determine our asymptote paths. And so what we're going to see here is when we actually look at the plot, you're going to notice that this pole is going to go towards infinity. This pole is going to be attracted towards this 0. And then these two poles, one's going to follow one asymptote up here and one's going to follow the other asymptote down here. And so remember, we can only make paths to the left of an odd number polar 0. So this is number 1. So the first path, it will probably follow along this asymptote. In the second pole, so that'd be path number 1 here. The second one here, it would then follow in the opposite direction. It's symmetrical still with respect to a real axis. Then this is the second one, so there should be no root locus after this second pole. Then the third pole, then the root locus should occur. So this one's going to go to the -3, this 0 here. Then going on, this is going to be the fourth, and so it's an even number 0. So there's going to be no root locus here to the left of it. This is the fifth. So this one, we're going to see that the root locus is going to go towards infinity. Sorry, negative infinity there. And so what we have is we determine the root locus, the path for each of these poles. And so now that we had all those determined by rule number 5, we're able to determine specifically which asymptotes they follow along and at what angle, and see how it's still symmetrical with respect to the real axis, the path of that root locus, and how it only breaks out at those left of the odd number is the only place where the root locus actually occurs. Nothing happens in between the left of an even number of polar 0. And now that we determined that, we're going to look at the next rule, which is going to say here for rule number 6, use the Roth-Hertz criterion to find the J omega axis crossing. And there is a hint here. For the hint, recall your row zeros. Okay, so within this, basically what we're going to look at here is, say that we're given that same one we had before here. So we have this same exact type of system for an example. And within this example, we're going to have to make the Roth-Hertz table. And so our transfer function, basically, when we made our transfer function, we saw that when we do our T of S here, we're going to get, so that's 1 plus L of S. Okay, when we had our 1 plus K, L of S equal to 0, remember, we were able to write this as 1 plus K, and then we had our 0 in the numerator all over, and then what was in our denominator were all of our poles, S times S plus 1 times S plus 2 times S plus 4 is equal to 0. Okay, now that we have that, you're going to see basically that when we need to make a common denominator, let me see here, when we have our transfer function, give me a second real quick. Okay, So this was determining when we had our open loop gain. So if we have this as S or S plus 1 plus. Yes. And so, okay. When you need to make the Roth-Hertz criterion, remember this is looking at our open loop gain, 1 plus K L of S is equal to 0. So now we're going to be working with, so after we got this, we plotted our zeros and poles because this is for the open loop. That's what we're able to plot is our open loop zeros and poles. So we were able to plot the open loop zeros and poles. And from that, you're able to make your graph. But in order to determine the J omega axis crossing, we're going to use our closed loop system. So the closed loop system T of S. For this one up here, your T of S is going to be KS plus 3, and then all over, and then in here, you're going to have in your denominator S times S plus 1 times S plus 2 times S plus 4 plus K S times 3. And so notice when you have to determine the J omega axis crossing, you then switch over to the closed loop system. And so in order to determine the stability here, remember, we look at our denominator. In our denominator, it's going to help us find those crossing points because remember, the Roth-Hertz criteria is to determine the stability. And so when there's sign changes, that means that it's going to, the number of sign changes means how many you have on the other plane. And so you divide it into the right half plane, left hand plane. So here we're going to be looking at our denominator in order to find out from this denominator here how many sign changes there are. And so here our delta S, our denominator, is going to be S times S plus 1 times S plus 2 times S plus 4 plus K S times S plus 3. And here, when you multiply this out, you're going to get S to the power 4 plus 75 S to the power 3 plus 14 S squared plus 8 plus K S plus 3K. Okay. So now we got it all multiplied out. And basically, after you multiply it all out, we're going to plug this into our Roth-Hertz table in order to check for the sign changes. And S4, S3, S2, S1, and then we're going to have an S0. So our S4, the coefficient's 1. Then the coefficient in front of the S3, 75. Then look at the next even number, it's 14. The next one down here is 8 plus K. Then we're going to have our 3K is our last one. Let's see. Yep. Our 3K is last one. Then here would just be 0. So using our Roth-Hertz criteria, we remember when we did this table, you're going to do the determinant. When you do the determinant, then you're going to take the negative of it. And so what we're going to get here is you'll get 7 times, let me see real quick. 70. Oops, I think I accidentally copied over 75. I meant to have this. Ignore the 5 here. That was my bad. I made a calculation error. So here you get 7 times 14 minus, and then it's going to be 1 times 8 plus K. So I'm just going to have 8 plus K here. All over, and then what's in the denominator there is 7. And then for our next one, here, right in the spot, sorry, it's a little crunch, it would be 3K in that second row. Now then, after you do the math, what we're going to have here in this denominator is it's going to become a little more complicated. We're going to have, when you work it all out, it's going to be 8 plus K times 14 minus, and then it's going to be 8 plus K over 7, and then minus 21K, all over 74 minus, and then it's going to be 8 plus K over 7. And that's looks a little crazy. And then in the second row, sorry, I don't have enough space to throw that in right inside the second row. Pretend this is the third row here. You have another 0. And so notice that here we have a row we're having our row zeros because we have this one term here, then we just have 0, 0 in all the other spots. Where in the row above, we had a term, then a 0, but here we only have one term, then we have it's followed by zeros. And so this would be our row of zeros right here, because after this term, we just have zeros for the other spaces. And so what we're going to do is this one up above is known as the auxiliary polynomial. It's the one that takes place before your row zeros. And so with that knowledge here, what we're going to see when we do the calculation is our 8 plus k and then times this whole numerator. If we get a row zeros here, this whole numerator had to be equal to 0. And so in order for this whole numerator to be equal to 0, basically what had to happen is 8 plus k multiplied by 14 minus 8 plus k over 7, and then minus 21k had to be set equal to 0. And when you solve for k here, what you're going to get is you're going to get k is equal to negative 74.6456. And then the other k value you're going to get is 9.6456. The main thing here is, remember, when we do our root locus, we're interested with the direction as k goes from 0 to infinity. And here, you'll notice that this is the only one that is from 0 to infinity. This one's in the negative range. So we are not interested in this k value. We're only interested in this one. And so what we're going to have happen is this. Basically, what we notice is in order to generate a row zeros, this numerator was set equal to 0. And because that numerator was set equal to 0, then it would generate row zeros here. This would be your auxiliary polynomial. So when k is equal to 9.6456, you'll have your Rothbert's table. So you'll have the S4, S3, S2, S1, and then S0. Remember, your auxiliary polynomial, if you plug in the k here of 9.6456 into this equation, you're going to get the value. You already know what your S4 is from up above. It's just 1, 14, 3, and then times, and then 9.6, and then 4, 5, 6. Because that's the k value we're interested in. Then we have our 7, and then this would be 8 plus, and then 9.6, 4, 5, 6. Then 0 would come down. Then this one here, if you plug in 7 times 14 minus 8 plus 9.6456 all over 7, you're going to get for this value 11.48, and then it's going to be 28 and then 94 when you do 3 times k, with your k being this value. And then you're going to have 0 here, of course. Remember, this is your auxiliary polynomial from up above. It's still in the x squared. So auxiliary polynomial. So you can write this as p of s is equal to 11.48 s squared, remember, because this is s squared, plus 28.94. And so when you take the derivative of this, you're going to get, this one will come down, so it'd be 22 point, and then this would be 96s. And so that is your derivative. And your derivative, then you plug into here, a 22.96s, and then the other ones are just 0. And then what you're going to notice is then for your last row, the 28.94, if you do the determinant and take the negative of it. And so now we got all those. And so we notice for our J omega crossing, notice that within this, there is no sign change now. So we notice that there is no sign change. So it is stable. So we have our roots are going to be on the J omega axis. So notice that we have all stable poles because there's no sign change. All stable poles. And for our J omega axis crossing, in order to determine where it crosses out of our real axis, we're going to look at the quadratic equation here, which is going to be our 11.48s squared, and then plus 28.94 is equal to 0. And so looking at that quadratic equation, because it's to the power of 2, when you solve for s using the quadratic, you're going to get s is equal to, and then it's going to be j 1.58. And this one right here, this is your omega, because remember, j omega. So this is your omega value, 1.58. And so now that we've seen that, where j omega crossing is, that's how we're going to be able to now look at the plot. And if we determined, looking back at, because we were looking at this one right here, where j omega crossing point was, does it make sense, basically, that we cross around omega equals 1.58, which when we look right here, this point where it crosses through in our root locus is at j 1.58. And this point right here, because remember, negative j 1.58. And that makes sense from our calculation here that we discovered where those j omega axis crossing points are, because those crossing points occur on that j omega axis. So that's why we were able to find out here where that specific value of omega is, where those crossing points occur. So to give a recap, when you do the Roth-Hertz criterion, find the j omega axis crossing, basically you look for your row zeros. So in order to get our Roth-Hertz to plug into this table here, we have to determine the closed loop transfer function. And so from our closed loop transfer function, we look at the denominator, and from our denominator, we plug that into the Roth-Hertz table. And then once we find basically a row of zeros, where we can adjust the numerator here so that it equals 0. So this term would become 0, so it'd just be 0, 0, 0. Once we get a row of zeros, then we're going to solve for the value of k that would make this 0. And so we found one k value that went from 0 to positive infinity. Using that k value, we plugged in back into this equation here, and we were then able to take our auxiliary polynomial, take the derivative of it, plug it into the Roth-Hertz table, and then determine that these are all stable poles that we have, but our j omega axis crossing is at the s squared. In solving for the value of s, where that j omega crossing occurs, we get 1.58, which we see here at j 1.58, and negative j 1.58 is where this root locus crosses through the j omega axis. Okay, now that we determined that, rule number 6, we need to find the breakaway and break-in points. So we're able to find the j omega axis crossing points, but we don't know where this root locus breaks out from. So that's the next rule we're going to look at. So for rule number 7, you're going to find the breakaway and break-in points. on the real axis. And so for the first step, you set k is equal to -1 over L of s. Recall, when you write it out, you do 1 plus k L of s is equal to 0. And so then if you literally just solve for k, it's going to be -1 divided by L of s. So that's how you get there. And then you let the denominator, so you let dk ds equals 0. So what you do is you take the derivative of this expression and you set it equal to 0. And then with that derivative, you find the roots. Okay. So what we're going to do here is basically, in order to solve this, going off that example we had here for the previous one, we're still going to go back to it. So here, we're able to write this as 1 plus k L of s is equal to 0, where we just have our open loop. And so for that open loop, if we move this over, we're able to write this as k is equal to -1 over L of s. And our L of s just plugging in is -1 all over. And then we're going to have s plus 3 all over here, which is going to be s times s plus 1 times s plus 2 times s plus 4. Okay. And so with that knowledge, basically, we're going to be able to move what's here in our denominator up to the numerator. And so because this is in the denominator here, and it's a fraction divided by a fraction. So this denominator, the bottom fraction, can move up into numerator. So we're going to get negative s times s plus 1 times s plus 2 times s plus 4 all over, and then we're going to have s plus 3 here. Okay. So now that we got that, for a value of k, we need to find dk of ds. And so in order to do that, we need to find the derivative of this expression here. So you have to take the derivative of this. And when you take the derivative of this entire expression, so that'd be negative s times s plus 1, s plus 2, s plus 4, and then all over s plus 3, you're going to set that equal to 0. You're going to solve for that derivative when it's equal to 0, and it's going to give you two values of s. When you plug that in, you're going to get negative 0.43, negative 1.61. And so these are your break-in, breakout points. What we need to look at is, do these two make sense? When you take the derivative and then you find the values where that derivative is equal to 0, you find those breakout or breakaway points. And so looking at R2, at negative 0.43, this makes sense where this one is at negative 0.43 because it breaks out. At negative 1.61, this one does not make sense. So therefore, it is not a breakout point because no breakout can occur to the left of an even number pole. Notice that we have 1, 2. So this one does not make sense. So this value of s does not occur, but this one does. This is a breakaway point. So you have to double check them to make sure that they make sense. Okay, now that we talked about that, basically, once you got your breakaway in your break-in points, the last one that we care about a lot for our rules are, how do we determine the angle of departure and the angle of arrival? So that's last rule number 8 here. So the angle of locus departure and the angle of locus arrival. arrival. Okay, in order to determine this, basically, you'll have your angle of L of S, which remembers in your open loop gain is 1 plus 2R times pi. And so you're going to have R is equal to 0, plus minus 1, plus minus 2. And then what we're going to see here is let's do an example in order to have a better understanding behind how do we actually calculate this. And so we're going to look specifically at an example here in order to determine the angle of departure and angle of arrival. So if we're given for this example an input R of S, notice here it's already given in the unity feedback system, so we don't need to convert it, but they give it the K they gave us multiplied by the G of S already. So S plus 3 here, and then S squared plus 2S plus 2. And then we have our output C of S. Okay, so what we can determine from here basically is if they ask us to sketch the root locus. So that was the direction, sketch the root locus. What we would do is basically going based off our rules is we are able to write this in the terms of our zeros all over our poles in this format. So we can now plot these onto an S-plane plot. And so when we do the plot of this, what you're going to see for it is when we do this calculation, we're going to have our S-plane appear as the following. We're going to have a pole at -1 plus J, then -1 minus J. Due to this term right here, we're going to have another pole at -3. Then we're going to have a 0 at -2. Okay, so now that we have that, now we have to determine, remember going back to our rules, we were able to write it, do this preliminary work where we're able to get in this format, and then we're able to plot our poles and zeros. So how many paths we're going to have? We have 1, 2, 3. We have 3 poles. So we're going to have 3 paths that we're going to have to take. So just so we know, just here off to the side, we have 3 paths because we have 3 poles in this graph. Remember, it's symmetrical, that root locus, so make sure you have that symmetry. And then what we're going to notice here is that the root locus is going to exist to the left of an odd number of pole or 0 on the real axis. So this is the first one right here, so it can occur right in between here, but it's not going to be to the left of it. And then our next one is our direction of our root locus is going to start from our poles and go to zeros or infinity. And then in order to determine what asymptotes we have, remember our asymptote, the sigma A, in order to determine where our asymptote starts out from, it's going to be the sum of the poles, which it's going to be at -1 plus J. So we're going to have -1 plus J. And then the next one's going to be at -1 minus J. So this is one pole plus -1 minus J. That's our other one. Then -3. That's where our third pole is. And then minus, and then where are our zeros located at? -2. Then all over the number of what we're going to have here is number of poles, which is going to be 1, 2, 3, number of zeros, which is going to be 1. So it's going to be 3 minus 1, n minus m. So you're going to get specifically -3 over 2. is going to be where your asymptotes occur. So that's going to be right at this point here, -3/2. -3/2. Now we have to find out the angle of those asymptotes. So the angle of the asymptote is going to equal, in order to determine that, you're going to have 2r plus 1 times pi all over, and then our n minus m is of course going to be 2 because 3 minus 1 is 2. So here, when you have r is equal to 0, you're going to get pi over 2. So for your theta A1, it's going to equal pi over 2 when r is equal to 0. Your theta A2, it's going to be when r is equal to -1. Here, it would be -2 plus 1, so it would be negative pi over 2. And then your theta A3, when r is equal to 1, you're going to have 2 plus 1, which is 3 pi over 2. Notice that this 3 pi over 2 is a repetition of pi over 2, so we can ignore this one here because it repeats every 2 pi. So these are the two angles of our asymptote. So we're going to notice that our asymptote, it's going to go positive pi over 2 from the real axis or negative pi over 2 from real axis. So these two poles here, what we're going to see is that they're going to approach this asymptote here at -3/2. This other pole is going to be directed towards that 0. And so right here, it's going to go towards that direction. So that's how we're able to sketch our root locus just based off those rules so far. Now, notice that we have no j omega axis crossing here. So we're not going to look at that in particular because notice it will never go through the j omega axis. So we don't need to apply that rule right now. In order to find our breakaway and break-in points, we don't have any breakaway or break-in points. Notice that it stays in the root the real axis, and it's not going to break out because these are already not on the real axis, these two poles here. The next one, for rule number 8, in order to determine the angle locus departure and angle of locus arrival, what we're going to have to do here is the big thing. In order to determine our angle of locus arrival and angle of locus departure, let's look at each one individually in order to find out where's it going. So right here, this is going to be a little harder, so you have to pay attention closely in order to have a good understanding of how are we going to be able to determine these. And so what I do first in order to find my angle locus departure is I'm going to label at this pole right here, it's going to be theta. And so we're going to get theta 3 here. So I'm going to label this one theta 3. Okay. And then I need to determine what are my other theta values. So my other theta values, I'm going to have an angle between this pole and this theta 3, this 0 and this theta 3, and this pole and this theta 3. So I'm going to have 3 other angles. So let me do that in a different color. So the first one's going to go from here. And I'm going to call this one from the -3 pole to this pole at -1 plus j. I'm going to call that theta 2 for now. Okay, and then the one from here to this 0, I'm just going to call that theta 1. It doesn't matter which order you do it in. And then the one right here from this pole up to that one, I'm going to call this angle theta, and then it's going to be 3. So, or sorry, theta 4, because we labeled that one theta 3 up there. Okay, now that we got that, so we have theta 1, theta 2, theta 4, all determined with location to theta 3. So we're going to see here that when we do our calculation, it's going to start out as negative theta 3. Notice that it's negative theta 3 because this is a pole, so it has a negative sign in front of it. For the 0, it's going to be plus theta 1. plus because it's a 0 here, then minus theta 2 minus theta 4 is equal to, and then the sum of all them. Remember, when we had it here, the sum of the angles is going to equal 1 plus 2r pi. So this is going to be 1 plus 2r times pi. Okay. So that'd be the sum. Remember, the angles for the poles are negative, where the angles for the zeros are positive. So that's why we had a positive for theta 1. So we set it equal there. And so in order to determine these angles, to determine the one we're trying to find is theta 3. So theta 1, we can determine that one. How much is it along the x-axis from this pole, from this 0 to this pole at -1? So from -2 to -1, we take one step. And so it's going to be tan inverse for theta 1. I'm going to write it down here. Tan inverse of 1. How much is it along the y-axis to get up to that pole? It's going to be one step. Okay. Then my theta 2, so negative theta 3. Oops. My theta 2 is going to be from here. So it's going to be two steps. It's from -3, -1. So it's going to be minus tan inverse, and then it's going to be along the y-axis, it's one step. So one step all over, and then two steps along the x-axis. Then my theta 4, it's going to be along the y-axis, 1, 2. So two steps, but it's going to be 0 steps along the x-axis. So it's minus tan inverse of 2 over 0. And then we're going to have that equal to. And so right here, we're going to set r equal to -1. So then if we set r equal -1, then we just get 1 minus 2 is going to be -1 times pi. So that'll be negative pi. I'm just going to write that over here because I ran out of room on that side. And so when you solve for theta 3, just plugging that into your calculator, you're going to get 108.4 degrees. And so the reason I chose r to be -1 here, why did I choose r to be -1? Because we have the angle of departure. So our angle of departure is, and the angle of arrival, remember that they're between -pi to pi. And so that's why it gave us a -pi. So from -pi to pi, that's where we want our angle of departure to be between. And so that's just because I chose, because if I chose 0 here, it would be pi, which is not including. If I chose -2, it would be -3 pi, which would not be included. So make sure you choose an r value such that it's included in between this interval. So that's how you would determine angle 3. Does that make sense? It has 108 degrees here. It's going upwards. So that's its angle departure. It makes sense that it's about 108 degrees from the real axis. And so that's how you would be able to determine your angle of departure if you did not know. Okay, so that's pretty much the whole summation of everything. So let's have a recap of the root locus before we move on. So when we're dealing with our root locus, it follows the various set of rules that we need to make sure that we follow. So for the root locus, the first thing is you want to make sure you have a unity feedback system. So within this unity feedback system, you're going to be able to write it in this equation form. 1 plus k L of s is equal to 0. Your L of s is your G of s in this sense, because if this were an open loop system here, it would just be your G of s. You would see why the gain here is just k times G of s, which that'd be the open loop. So you'd be able to write it in this format here. If you have to write the closed loop system, it's k G of s all over 1 plus k G of s. But you don't worry about this until the Roth-Hertz criteria for stability. So you're going to factor the L of s here in terms of your zeros and your poles. Then you're going to plot your zeros and poles, which you do. And so you get your open loop poles and zeros on a plot. Then you'll notice that rule number 1, the number of paths you have along your root locus are going to be equal to number of poles. We have 2 poles here. We have 2 paths you can take. It's symmetrical with respect to real axis, meaning it's the mirror image. When you flip it over this real axis here, sigma. And then because we're dealing with k from 0 to infinity, you're going to notice that it goes to the left of an odd number pole is where your root locus occurs. And now, number 4, the root locus is going to start from your poles and goes to your zeros or infinity. Then, in order to determine if it goes towards infinity, dealing with this case, rule number 5 applies, where it's going to be determined by the asymptote. So this was where your asymptote actually occurs is given by sigma A, and then the angle that asymptote you can find. And so it's the summation of your poles minus the summation of your zeros all over the number of open loop poles minus number of open loop zeros. And then here, what we're going to notice is that through this example, we were able to find our asymptote where these other 3 poles followed, because there's only 1 0. So only one of the poles could go to 0 where all the others went to infinity. Then we use the Rothbard's criterion to find the j omega crossing points, because this went for the j omega axis. And so in order to keep the stability, we want to keep the poles on the left-hand plane. So we want to find out where's this crossing point so we make sure that we don't go past it to remain the stability of the system. When you have to determine the stability, this is where your T of S comes into play. So you calculate then finally your closed loop transfer function for this system. The denominator, that closed loop transfer function, you plug into the Rothbard's criteria. Once you get 2 zeros in rows 2 and 3, and so on, the first one, you see if you can set it equal 0. If so, you'll get a row of zeros. So for that k value, to make that a row of zeros, you're going to plug that k value into your Rothbard's criteria, and you're going to solve for your s squared polynomial, solve the quadratic, you'll get the j omega crossing point. After you get the j omega crossing point, to find your break-in and breakaway points, you're going to set k equal to -1 over ls. You find the derivative of your k, and then once you get your derivative, you set it equal to 0 to get your real roots. You check the values of s against your root locus to see if they make sense. If not, then they don't exist. And so one of them made sense as a breakaway point, the other didn't because it's to the left of an even number pole. And then here, in order to find the angle locus departure and angle locus arrival, you look at one pole and you make phasors all leading up to that one pole. And then you're going to do the summation of all the angles, which it gives here, the summation of LFS. So the summation of all those angles you have in your open loop system of all those poles and zeros. Remember, you have a negative angle for your poles, a positive angle for your zeros. You sum them up and you set it equal to 1 plus 2r times pi. And the r has to be set equal to a value such that this value here on the right-hand side is between negative pi inclusive, but up to pi, not including pi. And then you'll get your angle of departure here for your pole. Remember, you get angles of arrivals for your zeros. Okay, that's pretty much everything there for the root locus chapter. It's a little bit broad. There's a lot of steps you have to follow, but it's very systematic in nature. And so now that we're able to determine the root locus, we're going to look at our next chapter, which is going to be examining the frequency response. So now looking at the frequency response, what should we be made aware of? So this one, I think it's hard for people because it's Bode plots, but there's a really simple technique that I use that might be a little easier than what the instructor taught you. So maybe you'll like my technique, maybe you won't. So just starting off, you're going to see that when we do the frequency response, the frequency doesn't change from the input to the output. So when you have specifically an input to a system, so say that your input f of t is equal to a magnitude, initial magnitude cosine omega t plus an initial phase angle, and it passes through a system. The biggest thing you're going to notice at the output of this system is that your frequency doesn't change at your output. So your x of t, it's going to have the same frequency. The only thing that's going to change here is your magnitude and your phase angle difference. And so you can call this, oh, sorry, they call it theta out just for the output and the magnitude output, but you'll notice that the frequency remains the same. That's why it's called the frequency response. So what we're going to be dealing with is that since it's implicit that the frequency remains the same, the only thing that changes is the magnitude and the phase angle. So a lot of times we like to write the magnitude and the phase angle in the phasor form as the input to the system, because those are the only two things that change and everything else remains the same. So you'll notice that your output is going to have a new magnitude and new phase angle. Okay, so now that we talked about that, you're going to notice that this block right here is called the system frequency response. And so your system frequency response is going to be given by G omega. Notice how we're just dealing with frequency here, and this is going to have a magnitude part and a phase part. And basically your system, remember, you can calculate it as the output over the input. So we're going to have the output over the input, which gives us our system transfer function, which you remember when we calculated transfer function, it was output over input. Here we're doing system frequency response, output over input, and that's how you get the frequency response. So it's very similar in nature. And so what you're going to see here, the magnitude frequency response here, we're going to get when you just calculate the magnitude of this response, it's just MO over MI. When you calculate the phase frequency response, it's just the phase of the output minus the phase of the input. Because remember, for the phases, you subtract them when you see it in the division here. Okay, so now that we talked about that, what I want us to see is oftentimes we see the system in the S plane. So here it's X of S, and then it passes through our system frequency response G of S, and we get our output Y of S. So we're used to seeing it in this block diagram format. And what we're going to notice is that your G of S, you can calculate it. It's just the output Y of S over the input X of S. And your magnitude frequency response, because remember, S is complex frequency. It has the sigma, which is the real part, plus J omega, which is your imaginary part. So your magnitude of your frequency response is going to be given by the magnitude of the output over the magnitude of the input. And then your basically, in order to determine the phase frequency response, it's going to equal the phase of the output minus the phase of the input. Okay, so now that we determined that, remember, this is S, but we like to work with pure imaginary frequency. Pure imaginary frequency means that when our real part's 0, so we just have J omega. So we get G, J omega, just plugging in for S, J omega. Then it's going to be Y, J omega all over X, J omega. Okay, so since we determined that, we were able to write it in this equivalent format because we just work with pure frequency. What you're going to notice is that we're going to plot this. And so for the frequency response, what they like to do is there's two types of plots. So for plotting the frequency response, you can plot it on two different types of charts. The first one is known as the Bode plot. And so for the Bode plot, it's going to be, the first one is going to be a plot of 20 log GJ omega versus omega. So that's the magnitude frequency response. And then you're going to plot the phase frequency response, which is going to be the phase of GJ omega versus omega. Okay. And then for your Nicholas chart, basically, oh wait, sorry, it's the polar plot, which is the big one. Ignore the Nicholas chart, that one never pops up. You don't need to know it. Polar plot, basically for the polar plot, it's going to be the real part of GJ omega, so GJ omega, and the imaginary part of GJ omega. Remember, imaginary is always along the y-axis, real part's always along the x-axis. So you're going to plot this in one graph. So notice you have two graphs for your Buddy plot. You have a magnitude frequency response and a phase frequency response. Whereas for the polar plot, you have a real and imaginary part. You have it embedded in one graph. Imaginary on the y-axis, real on the x-axis. So what we're going to look at is we're going to do a bunch of examples for plotting because you have to be very familiar with the plotting techniques. And I want to go over my tips in order to understand how to plot it because I think it's a lot better than how he described it. So when you're working with Bodhi plots, there's a few general rules that you should know. So for the magnitudes, basically each pole contributes -20 decibels per decade. So when you have a first order system, you only have one pole, so you have -20 decibels per decade. When you have a second order system, you have two poles, so it's -40 decibels per decade. And so each zero, though, contributes +20 decibels per decade. And so just know that the zero is the opposite effect of the pole. And then for the poles, also notice, so this is for the magnitude plot. So just know this is for your 20 log of GJ omega plot. But when you have to deal with the phase, each pole contributes -45 degrees per decade, 1 decade before and after. So basically your pole in the magnitude plot in zero, once it hits that frequency, it starts falling -20 decibels per decade or +20 decibels per decade up to infinity. But each pole in the phase plot, it only contributes -45 degrees 1 decade before it's supposed to occur at that frequency and 1 decade after. And so each zero then contributes +45 degrees per decade, 1 decade before and after that omega value, so that frequency where it should occur, before and after. So we're going to do an example now. So this is dealing with our phase plot. So this is with the phase of GJ omega. Okay. So from our Bodhi plot, let's do an example. For this example, we're going to have G of S is equal to 1 over S plus 2. And so basically, he wanted the magnitude and phase responses of this, which you can do. I'll show you his way and then I'll show you my way. So he asked for the magnitude and phase response, and he wants it in the equation format. So the magnitude response, in order to find it in the equation format, you're of course going to do G of S evaluated at S equals J omega. You're going to get 1 over J omega plus 2. And when you have to find the magnitude, it's going to be 1 over square root of omega squared plus, and then 2 squared, which is 4. And then when you have to do the phase of GJ omega, it's going to be tan inverse, and then in the numerator, you'll have no imaginary. So it's going to be tan inverse in your numerator. There's no imaginary component. It's just 0 all over real part 1 minus. And then what you have in the denominator, tan inverse of your imaginary components, omega over 2. And so you're going to get here, it's going to be minus tan inverse because this one would just be 0. This one would go to 0. And then this one's going to be omega over 2. And so you can plug in frequencies to determine the response here at each value. But what I find easier is we know in here, we have one pole at s equals -2, which you're going to notice this is actually, how do they write it? When we do this on the plot, we work with our, they like to call this more of the, they like to normalize this equation here. That's my best terminology for it. So they will normalize this. So they will do a normalization. And what do I mean by normalization? It's so you get a s plus 1. And so they'll divide. So they're going to do 1 over s over. And if you divide this whole denominator, if you factor out a 2, it would be s over 2 plus 1. And so here, what we're going to see then is this would be divided by 2 over 2. 2 over 2. Which would be, yes, because this would be 0, 1 over 2, 0, which would be 1. Let me see real quick. If we multiply this by, divide by 2 over 2, that would be multiplied by 1/2 or 1/2. Yeah, okay, so this should be a 2 in here because that would be multiplied by 1/2 over 1/2. So you get a plus 1 here. So what we're going to look at for the magnitude plot versus the phase plot is from this equation, how can we determine the magnitude and how can we determine the phase? So you're going to look at each one of these individually. So notice in our numerator, let's look at this one first. So when we're having to do the magnitude and phase plot, this one for its magnitude, remember your magnitude plot is in terms of 20 log and then GJ omega. So the numerator is 20 log of 2. And then in your denominator here, which is our other one right here, it's going to be minus 20 log because it's minus because it's in the denominator. And then it's going to be s over 2 plus 1. What we're going to see here. But the big thing that we have to deal with here is this one is when we plot it, 20 log of 2. When you put that into your calculator, it's going to be, let me pull it up here. It's my calculator, 20 log of 2. And then see how we get 6.02 here. And so what we're going to see with our graph actually, move frequencies, wave attenuation. We're going to get specifically our plot to be, what did they have, minus 20? Where this one is going to be frequency 2. Okay, but we'll see in our plot then for this, because if we have 20 log of GJ omega, this one would be the one that contributes, the other one would stay the same. So I would see that this one would be a constant value, which we're going to notice in the beginning. So this one's nice because it's a constant value. However, this one is going to change because notice that S, this is our J omega, which when this omega changes, because our Bode plots, they're represented in terms of omega. When omega increases, this is going to have a more significant impact. This value is going to become larger, so this is going to take on a larger impact. But notice that this won't occur until its corner frequency. And so what we're going to notice is that the 2 here in the denominator is going to tell us that's the corner frequency for the normalization. And so right here, this is the corner frequency at which it's going to occur. And so that's what we're going to have to be looking out for when we do our plot. So let's now draw out the plot. Oh, let's just do the phase real quick while we have the phase still with us. Notice that we only have a pole. We don't have any zeros. So the only contribution to the phase for GJ omega, we're just going to have one pole here. So notice that our corner frequency was at 2 when we did the normalization. This became 2. So we're going to have negative 45 degrees per decade starting at, and then it's going to be 1 decade before omega equals 2 and up to 1 decade after omega equals 2. So remember, each pole contributes negative 45 degrees per decade, 1 decade before the value and 1 decade after that corner frequency. And so now when we do the plot of the 20 log, so this is the 20 log of GJ omega. And then when we have our omega here down on our x-axis, and then we're going to have the other plot, which is going to be the phase representation. So the phase plot is normally just phase in degrees. And it will have the omega value under it as well. And what we're going to see here is for this, it's a log plot. So it starts at 0.1, goes up to, here's 1, here's 10, and here's 100. Here's 1, 10, 100. And this is 0.1. So what we're going to see is specifically, we're going to notice that it's negative 45 degrees per decade, 1 decade before omega equals 2. So this is omega equals 2. So 1 decade before would be at 0.2. So right here at 0.2, we're starting at 0 degrees. So at 0.2, it's going to go 1 decade after negative 45 degrees here. So negative 45 degrees per decade. So from 0.2 to 2, negative 45 degrees in between. And then from 2 to 20, that's 1 decade after, it's going to continue and have negative 45 degrees. So this line is negative 45 degrees per decade and went 1 decade before and 1 decade after, and then it will stop. No more contribution. So it's going to remain at negative 90 degrees. There's no other poles. So that pole contributed negative 45 degrees before and negative 45 degrees after. Okay, so we did the phase plot now. Now, when we have to do the magnitude plot, notice that we have a constant value here, but we're going to have this one's going to take mostly effect at the corner frequency value of 2. And so what we're going to see with this one, just like in others, give me a second just to check it against what I have here. Let's see if I had an example to show you guys, but it's fine if we don't. Okay, so basically here, notice that each pole, we have a constant value here in our numerator. And so due to the constant value, we're going to be looking at all that. So your calculator, you're going to see that 20 log of 2 is approximately 6.02, what we have here. And so when it starts out, it will be at 6.02. And then at this corner frequency of 2 here, that's when it's going to start to decay by 20 decibels per decade. So at 2 here, it's going to be constant all the way. So 6.02, but at 2, it's going to start dropping negative 20 decibels per decade. So say this is negative 26.02 decibels. It would drop then negative 20 decibels per decade and continue to drop at that same rate up to omega equals infinity. So you'll see that for the phase one, it only goes negative 45 degrees per pole, 1 decade before and 1 decade after that corner frequency. Where for the phase plot, once it hits that corner frequency, it's going to contribute that pole negative 20 decibels per decade up to omega equals infinity. But it will be constant beforehand, then it contributes. And the only way you can cancel this out is if you have a 0. So it would contribute positive 20 decibels per decade. Okay, now that we saw that for the first time, let's do another example with it, just so we become more familiar with it. So we're going to draw the Bode plot. So for this example, draw the Bode plot for G of S equals 1 over S over A plus 1. Notice that they already normalized it, so it's a plus 1 for S term. And so this is already normalized, which is very nice. So they were able to get a plus 1 at the very end, which we like. And so in order to do the specific Bode plot, you look at the numerator and denominator. So we have no zeros in numerator, but we have a constant. And so for a magnitude plot of GJ omega, 20 log of GJ omega, it's going to equal, here we're going to have 20 log of 1, and then minus, and then our 20 log of S over A plus 1. And then for phase of GJ omega, it's going to equal, in our numerator, it's going to be 0 degrees, of course, but then we're going to notice that we're going to get minus, and then it's going to be tan inverse, and then this would be omega over A, tan inverse omega over A, because once you substitute in J omega, be omega over A, and then the real part would be 1. So be omega over A over 1, which is just omega over A. And so doing the plot of this, though, for the magnitude plot, a 20 log GJ omega, and then the phase plot of GJ omega, what we're going to see here specifically is for a magnitude plot, 20 log of 1 in our numerator is 0. So this part is just 0. So we're going to start out at 0 decibels per decade, and we're going to go up to A. So let's say this is the point where it's at A. That's the corner frequency A. So then it's going to be at 0 decibels per decade. But once it reaches A, so this would be 0 decibels. Once it reaches A, it's going to decline at a steady rate of negative 20 decibels per decade, because that was the cutoff frequency, sorry, the corner frequency right there. But our phase plot, well, we see it's minus tan inverse of omega over A. And our corner frequency is at A. And so that's where 1 decade before, so that would be at 0.1 A, and 1 decade after, it's going to have, so this would be at 10 A, we're going to have negative 45 degrees. So this would be negative 45, to negative 45. And then it's going to be constant otherwise. So if it started at 0 degrees, and then it goes down negative 45 degrees in 1 decade. So at this point, the midpoint, and it's negative 45. Then it goes down another negative 45 degrees. So by the second time, it's negative 90, the original. And so that was the contribution due to that one pole. So that's how we got our plot here. And this slope is negative 45 degrees per decade due to that one pole. So that's how we were able just to determine it. You can write the magnitude and the phase part, but it's just easier, I think, if you know, okay, I only have one pole. So therefore, at that pole value, it's going to be negative 20 dB per decade. And I'm going to have that one pole contribute negative 45 degrees 1 decade before and 1 decade after that corner frequency. You just have to make sure it's written normalized in that you take into account for the magnitude and the phase, the constant up there. Know that the constant is just 0 degrees for the phase, but for the magnitude, just watch out in case it's any number other than 1. Now we're going to look at a second order system in order to understand, or let me see, 20 log. Okay, this one, I don't think you'll see, but this one for sure, I think this one's a good one to right before the second order systems. I think this is nice to have so that you see how you can have multiple poles and zeros. So for this example, it says draw the Bode plot for G of S is equal to S plus 1 all over, and then S plus 0.2. So what we need to do is for the magnitude, which is 20 log of GJ omega, for that plot, what we're going to see is it's going to be, what we need to do first is we need to normalize this denominator so we get an S plus 1. Notice our numerator is normalized to S plus 1 for a first order system, but the denominator isn't. So we'll divide everything by 0.2. So we're going to get, in our numerator, it's going to be 1 divided by 0.2 times S plus 1 all over, and then divide denominator by 0.2, you're going to get S all over 5. And then because 1 divided by 0.2 is going to be 5. And then what we're going to have here is plus 1. So we normalize the denominator, and now we're going to look at each contribution equally. So we're going to look at the contribution by the 1 over 0.2, which is 5, of course. So we're going to look at 20 log, and then of this part right here, which is 1 over 0.2, which is just 5. And then in the numerator, we also have this part right here. This 0 is already normalized. So it's going to be plus 20 log, and then it's going to be a GJ omega, which here, if you look at it, it's going to be then our J omega plus 1, but that'd be omega squared plus 1. So I'm going to just call this 2. Just know that this one has a 0, which will contribute a positive 20 log. And then here we have a pole for this denominator. I'm going to call this 3. So it's going to be minus 20 log, and then where that cutoff or the corner frequency is for 3, which is at 5. Okay. Now that we determined that for our magnitude, we have to look at our phase, which is the phase of GJ omega. Our phase of GJ omega is going to equal, the phase of GJ omega. Notice in the numerator, this is going to be 0 degrees due to this term, but here we have a 0, which this one would be tan inverse. Because it's a numerator, I don't have a negative sign because it's a 0. And then the imaginary part would be omega over 1 minus then the tan inverse denominator. It's going to be 1. It'd be omega over 5 over 1. So just omega over 5. And now if we make the plots, what you're going to see is doing the plots of these, we're going to have the following. There we go. Okay, omega is on our x-axis. We have 20 log of GJ omega for our magnitude plot. And then we're going to have the phase of GJ omega. So this would be in degrees. Okay, so in order to plot this, you're going to notice specifically that our magnitude plot 20 log of 5. That's a constant value that remains, so 20 log of 5. We're going to have 13.98, it looks like, where we're going to start out at. So we're going to start out at 13.98. And so until omega equals 1, so that's going to be where the first corner frequency is at. So at omega is equal to 1. So it's going to stay at this value until omega equals 1. And then it's going to start to decline. So maybe I should show it in this color here with negative 20 dB per decade because, wait, sorry. It actually increments because that's a 0. It's not a pole. So it's going to increment by 20 decibels per decade. So let me erase that real quick. Notice that zeros, remember, they're plus 20 log per decade. So at this point, it's going to start increasing at positive 20 dB per decade. But then once it hits 5, so once it hits omega is equal to 5 here, then it's going to oh, notice that notice that I made an error here, which you need to be careful about as well. When you divide by 0.2, you're going to get s over 0.2 because 1 divided by 0.2 gives you 5 here as the coefficient in front, but 1 divided by, if we divide by this by 0.2, it remains 0.2 in the denominator. So 0.2 in denominator, that actually would come before the 1. So here, what we're going to notice, due to this term right here, at 0.2, let's say it's like right around here, 0.2, we're going to be going down negative 20 dB per decade until we get to omega equals 1, where it's going to then flatten out. This would be positive 20 dB per decade. And so that's why, because when you divide by 0.2, you have to keep the omega value in the denominator, the s, because that's where the corner frequency occurs. You can't put it in the numerator because that's the normalization. So now that we have that, we need to look at the phase. In the phase, we have a 0, which will contribute positive 45 degrees per decade, one before and after the corner frequency. But we have a pole, which will contribute minus 45 degrees per decade. So at 0.2, 1 decade before, it's going to already have negative 45 dB per decade. So coming in from, if we look at, it would be 0.02. Okay, I'm going to minimize this so it looks better. This is not following the exact of a log plot because I just want to show you guys what it looked like. And we'd have 1, which one would be 0.1. Okay, so then we'd have 0.1, let's say 0.2. Then we'd have 1 decade after, which would be 1 and then 2. And then we'd have 10 over here. Okay. So 1 decade before 0.2, we're going to notice that because that's where this corner frequency is, it's going to have negative 45 degrees per decade. So it's going to be going with negative 45 degrees per decade. But once it reaches 0.1, which is 1 decade before 1, which is the other corner frequency, it's going to hit a positive 45 degrees per decade. So then it would cancel out the effect because this would be plus 45 degrees per decade due to that 1 decade before. This one's 1 decade before the 0.2, so it's negative 45 degrees per decade. Then at 0.2, then we still have this where it is the same, but this one would be negative 45, negative. Okay, so this one would then cancel out until we go all the way over here where, so this would remain at negative 45 dB until the effect, so this would be 0 until right here where the 2 will die out because it's 1 decade after, so that negative 45 degree per decade by the 0.2 where omega equals 0.2, that will die out. So then this one will start to be able to take on the positive 45 degree per decade until 1 decade after, which is at 10. So then it goes positive 45 degrees per decade. So basically, 1 decade before 0.2, which is the corner frequency of the first one to come, it contributes negative 45 degrees per decade. But 1 decade before 1, which was the 0, it contributes positive 45, so nulls out the effect of the other until 1 decade after 0.2, we're going to notice the negative 45 degrees will cancel out. So it will start only doing the positive 45. But 1 decade after 1, we're going to see that it's going to then flatten out and then it will remain at that value. So pretty much that gives you an understanding behind those Bode plots. So now that we've seen all that, we need to look at second order system Bode plots and how they contribute. And so what we're used to is in Bode plots, we're used to the normalization of first order systems. And so when we did the normalizations of first order systems, the biggest thing that I told you guys was that you have to get your S over omega n plus 1. But when you work with second order systems, you're going to notice for the normalization of second order systems, you're going to have to follow S over omega n squared plus 2 zeta S over omega n plus 1. And so just like we had normalized here, you get a +1, you have to normalize this one, get a +1. And so what we're going to deal with is we're going to see an example where you have to normalize a second order system in with the pole, but to be careful, just giving you a heads up, this is going to be your damping ratio. Remember your zeta here. And so based on your zeta, you're going to have to look at how much air does it contribute, because a zeta of 0.1, it will diverge and it will have like a little over, like, remember how it goes a little bit over what it's actually supposed to be getting down here. So you're going to have to account for that air. So you have to watch for zeta to account for any air. And we're going to look at that in an example. So see why we should be looking at it. So let's do one right now. So for our example, we're going to have G of S is equal to 1 over then S squared plus 2S plus 25. First thing I would do is normalize. So in order to get a +1 here, I'm going to divide everything by 25. So I'm going to get a 1 over 25 in my numerator, all over, dividing denominator by 25. I'm going to get a 1 here, so +1. But 2s over 25, I'm going to get 2, and then my omega n value is going to become S squared over 25, which we're going to have S over 5 here squared, because that'll give me S squared over 25 if I divide, plus 2. And then we're going to have our S over 5. And then this, in order, our zeta must be 1 over 5. So that would give us 2 over 25 times S. Oops, I think my S is lacking. I'm just going to add it right there. So we had to divide everything by 25 in order to normalize to get a +1 here. And then we notice S over 5 squared gives you S squared over 25, which when you divide by 25, S squared over 25, I just factored it out. Then plus 2. And then what is your zeta here? It would be 1 over 5, since your S over omega n is 1 over 5. And so now that we got it written in that format, oh, sorry, this is why. It's the 1 over 5 for your zeta times S over 5. So this is 1 over 5 for your zeta times S over 5, then plus 1. Okay. Now that we got that, we have to look at each one individually. And so this is a constant in the numerator, so we can look at this one. So for our 20 log of GJ omega, we're going to look at the numerator, which is going to be 20 log of 1 over 25. And then we're going to look at denominator. Denominator here, it's going to be minus 20 log, and then I'm just going to call this a 2 because actually it's a second order system. So remember, this has 2 poles, so it's actually minus 40 log, correct? Because there's 2 poles because it's a second order system. So it's going to have minus 40 because each pole contributes minus 20 log. Okay, now for our phase plot, it is the phase of GJ omega, which is going to equal, looking at that numerator there, this is no imaginary term, so it's going to be 0 degrees minus tan inverse, and then this is going to be of number 2, which what we're going to see here, because this is a second order system, it has 2 poles, so it's going to contribute minus 90 degrees per decade, one before the omega n and one after the omega n of 5. And so for our magnitude plot here, we're going to see for the 20 log of GJ omega, you're going to notice that this one is going to start out at 20 log of 1 over 25, which is 20 log of 1 divided by 25. You're going to get negative 28 about. So you're going to start out negative 28 dB. And then up until omega is equal to, well, the omega n here is 5. So when omega n is equal to 5, you're going to start going down negative 40 decibels per decade. And so you're going to remain at this negative 28 until you reach that point. Then you're going to go down negative 40 decibels per decade. So say that this is this is 50 right here, because that would be 1 decade. And so this would be at negative 68 decibels because it's negative 40 decibels per decade. So it declines at a faster rate because of the second order system. But what we're going to notice for our phase is, this will be interesting, is for the phase plot, what you guys are going to have is 1 decade before and 1 decade after. So this would be at 0.05, then we'll have 5, and then we'll have it go to 50. So 1 decade before, so say that it starts at 0 degrees, which it does, it's going to go down negative 90. And then it's going to go down another negative 90. So it's going to be negative 90, then it's going to go down another negative 90 each decade. So it's going to reach negative 180. And so that would be the contribution of a second order system. It's negative 90 degrees per decade, 1 decade before and 1 decade after the omega n value. And so that's what we see here from 2 plots. But with our magnitude plot, because this had a zeta value of 1 over 5, since zeta equals 1 over 5, which is 0.2, we have to take into account the error, which the error right here, it looks like it goes about almost 1, like 10 decibels up. And then, so what you're going to have to do here is you're going to have to show that you took into account the error by going about like 10 decibels up, and you'll say that this is due to the zeta. So adjusting for the error due to your zeta, because your zeta equals 0.2. So that's the only caveat with second order systems. You have to watch out for your zeta value to determine how much overshoot there is at that omega n value. And so now that we talked about that, that pretty much gives you everything you need to know about the frequency response of Bode and your Bode plots. And if you have to do a polar plot, your polar plot, you basically would, from your G of S, let me see if I have a good, yeah, here's one. Okay, if you have to make a polar plot, if he asks you to do this, so for an example, find the polar plot. You have to get the real and the imaginary part of your frequency response. So of G of S is equal to 1 over s plus 2, what you're going to do is you're going to find the real part and the imaginary part. So you're going to do g of j omega, substitute in j omega for s is equal to 1 over j omega plus 2. And then you're going to do multiply by the conjugate. And you'll multiply the conjugate, so you'll have no imaginary terms in the denominator. So you're going to get j omega minus 2 all over. Then this would be a minus omega squared and then minus 4. And then what you're going to see is you can separate this into two different fractions. 2 over omega squared plus 4. Then if you pull out, basically if you pull out that negative sign in the denominator up to numerator, you would get minus j omega all over omega squared plus 4. And so this would be your real part of g j omega right here. This is the real part of g j omega, where this is your imaginary part of g j omega. And so that's what you would use in order to plot it. So then you would plug in values of omega in order to do your polar plot of the omega, the real part of j omega. So when you would plot it, you would plug in values for your omega, and you would plot on the x-axis the real part of g j omega, and then you would plot on the y-axis your imaginary part of g j omega. And when you do that, you would get a graph that sort of looks like this, and the omega values are embedded. So for each value of omega, the frequency here is embedded because that represents at that frequency what the real part is and what's the imaginary part. So the frequency is embedded. So that would be how you would make the GJ omega plot, by looking at the real part and the imaginary part. And from this, you're able to graph your polar plot. You plug in values of omega in order to determine what's my real part value and what's the imaginary part value. So those would take a long time. So I don't see that being tested on. But the big thing, what we notice with the polar plots and the Bode plots, is for the Bode plots, what you really need to know is each pole contributes negative 20 decibels per decade. Each zero contributes positive 20 dB per decade. Each pole contributes negative 45 degrees 1 decade before and after that omega n value. And then each zero contributes positive 45 degrees per decade 1 decade before and after omega n. And so now that we have that, you're going to see that I like to normalize it. And so in order to do the normalization for the first order systems, you get a +1. So then it's just S over omega n. For this normalizations of the second order systems, you're going to get it in this format, and you have to watch out for the zeta value in order to account for the error in the magnitude plot. That's pretty much the whole run through of Bode plots in the frequency response. And then we're going to move on to the Nyquist. And so for the Nyquist, it's going to work with complex functions. And so it's very big on stability. So we're going to look at how complex functions take into account with the stability. So second real quick, let me pause. So in order to do the Nyquist, what we're going to see is that first we're going to start out with mapping. And so we like to start out with mapping because it gives us the contour plot. And so let's look at an example. So say that we have our f of s is equal to s over s plus 2. And so it wants us to evaluate f of s at points A, B, C, D. And so they give us a plot of the S plane. And so for a plot, you'll see that it goes 1, it goes up to j, it goes -1, and then we're going to have -j. And then we're going to have here, this one is A, here we have B, here we have C, here we have D. And what we're going to notice is that this path basically here we call a contour. And so it's going to go down here, 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 here. That's the general direction. And then when we're translating it, notice that we're going to take this from, it has the complex plane here, and we're going to translate it over to another complex plane because we're going from 2D over to 2D. And so this would be the U, and this will be our V. And so in order to translate points A, B, C, and D, let's look at it. So A, if we look at the magnitude, specifically, if we make a vector, if we take the magnitude of the square root of 1 squared plus 1 squared, we're going to get rad 2 angle 45 here. And so if we do rad 2 angle 45, if we're going to plug that into our f of s, if you plug in here, f of s is equal to, and then what we're going to have here for our specific one is it's going to be, let's see, if we plug in 1 plus j all over 1 plus j plus 2, you're going to see that rad 2 divided by rad. Divided by rad. Oh, okay. Notice here that we have a 0 at 0. So sorry, let me erase this real quick. If you were to plot this, he would want you to plot the 0 at 0, then he'd want you to plot the pole at -2. And what he's going to want you is right here to A, just like we did before, we had rad 2 angle 45. But for the other one from -2, which is part of your complex function, this one, if you find the magnitude, it's going to be rad 10 angle 18.4 degrees. So remember, what it's going to be like is we have two phasors. One comes from a pole right here, and one comes from a 0. Remember, your zeros are in your numerator. So your new value for your A, it's going to be your rad 2 angle 45 degrees. That's in the numerator all over. What's your pole at? Rad 10 angle 18.4 degrees. And so when you solve this, it's going to be 1 over rad 5 angle 26.6 degrees. And so that's what we're going to see here is if you make that vector, it's going to be right around here for your A. And then if you do the same thing here, you draw another set of phasors that go from the pole and 0 of your f of s, and then you do the calculation to get the magnitude and the phase, then you're going to notice that it's going to end up over here, and you're going to get your B value. And then if you do your C value, you're going to get it over here. And then if you do your D value, so it's going to be the following plot once you connect it in order to form your new contour. And so it would go from here, and then you would have it going all the way over here. From here, it would go this way, and then it's going to go up this direction. So it's going to follow your contour plot and look just like that. And once you plot all of them, if you went and you made the phasors for every single point along this contour, and you did this calculation, your contour plot would look like this blue outline here if you plotted all the phasors. But that would take a lot of time, just so you know. What we like to do is we look at the mapping. So what we take is a contour, which we see outlined by the green here, in the S-plane is mapped to a contour, which we see in the blue outline here, which this is called, here on the left, it was the S-plane. And this is called the f of S-plane on the right-hand side. And so now that we saw that, there's an important to deal with. And so this argument is called the I feel like I'm mispronouncing this, so sorry. The Cauchy or Cauchy argument principle. It's okay. We make mistakes, so I don't know how to pronounce that. If the contour is in the S-plane, what we're going to see, what his principle basically says, if contour C of S, and when we refer to C of S, the S refers to the S-plane. So it's talking about this contour in our S-plane. So you can call this the contour in the S-plane is known as C of S. So in the S-plane, I'll just put it here too. If the contour is in the S-plane and it encircles Z zeros and P poles of f of S. So notice how this contour encircled a pole. A zero, but not a pole. The pole was outside the green contour, but the zero was inside. So the next thing is it doesn't pass through any poles or zeros of f of S. Notice that this contour, it doesn't pass through any poles or zeros in its outline. And then the third is the traversal in the clockwise direction along the contour. So notice how our contour in the S-plane, it goes clockwise by the arrows. It goes in this direction along the green outline. It's clockwise. So then the contour in the f of S plane, which we have here outlined in blue, is going to encircle the origin of the f of S plane n times in the clockwise direction. So they call this contour C of F. Then C of F, which is the contour in the f of S plane. So in the f of S plane, encircles the origin of the f of S plane n times in the clockwise direction. And that would be given by n equals z minus p. So n would be the number of encirclements. So this would be number of encirclements. Z would be the number of zeros inside the contour. So in our example here, that would be 1. Or wait, sorry, inside the contour. This one's actually unknown because this refers to our closed. Let me see. This is 1, 3. Yes, that would be the number of zeros inside the contour, where this one would be the number of poles inside the contour. So for the example above, what we see is n is equal to z. There is 1 0, but there are 0 poles inside this contour, so it's going to equal 1. And what we see, it did encircle the origin 1 time. So that makes sense. So, and notice that is in the clockwise direction. So this one's in the clockwise direction as well. Now that we talked about that, we're going to look back at our feedback system. That's going to help us in order to determine what we need to look for when we're trying to determine our stability. So what you're going to be familiar with is 2 types of systems. You have an open loop system, and we have a closed loop system, just like we talked about at the beginning of this lecture. Okay, so for the open loop system, you're going to notice that you get your G of S here, and then you're going to have your H of S down here. But you never close the loop, so that's going to come into play a little later. Where when you have your closed loop system, you have your input, just like here, your R of S. And it goes through, though, adder, because you'll actually have feedback because you closed it. You'll have your G of S, which would be your forward path gain. Then you have your H of S down here. And then you're going to have your output C of S. So for this, your transfer function here, T of S, is going to be given by G of S all over 1 plus H of S, G of S. So this one here, you're going to notice that we're going to call the open loop gain G of S times H of S. And so this will often refer to down here in this denominator. The H of S times G of S is known as the L of S, which is the loop gain, the open loop gain, which we see right here, because when it's open, the gain is just G of S times H of S. So that's where it comes from. So we're going to look at the open loop and closed loop poles. And so open loop poles and closed loop poles. So looking at the open loop poles, where it's going to be is, remember, for open loop, we're going to have L of S is equal to G of S times H of S. And so what we're going to see here, H of S times G of S, we're going to say that our, remember, H of S can be expressed as the numerator of H all over the denominator of H. G of S can be expressed as the numerator G all over denominator G. So in order to find the open loop poles, that's when the denominator is going to equal 0. So that's when D of H times D of G would equal 0. For the closed loop here, you're going to notice it's going to be when you rewrite this in terms of what we had here, our this would be energy times, then we have D of H. So this would actually become energy times D of H all over dg dh plus ng nh. If you do the fractions and simplify, you will get that. So your closed loop poles are when D of G, here, D of H plus ng n of H is equal to 0. But your open loop zeros and closed loop zeros, what you're going to get here is you're going to see that your open loop zeros are when your n of H energy is equal to 0. And when your closed loop zeros, it's when ng d of H is equal to 0. Okay, so now that we got that, you're going to be able to tell that in order to determine our f of s, which is this entire denominator here, is, remember, we like to look at stability. So under what condition is this system stable? And that's when our denominator, we're going to see when it equals 0, that will tell us then before when it is stable. So we avoid that right-hand plane. And so what we're going to be able to tell here is the 1 plus H of S, G of S must be equal. What we're going to see here are f of s. They define as 1 plus H of S, G of S, which we're going to have as 1 plus, and then remember, this is n of H, n of G, all over, and then we have d of H, d of G is equal to, and then what we're going to see here is we want to set this equal to 0 for stability reasons. So here, if we get a common denominator of d of h dg, we're going to have d of h dg plus n of h ng is equal to 0. And so in order to ensure that our system is stable, basically what we're going to do is our zeros of f of s. So the zeros of the f of s right here, this reminds you guys of when this is set equal to 0, isn't this the exact same thing as the closed loop poles? But when our denominator here is equal to 0, that's going to match the open loop poles. And so what they like to say is the poles of f of s, which are right here, the dhdg, are the poles of the open loop system. Whereas the zeros of f of s are the poles of the closed loop system. And remember, we're always interested in our closed loop system and our stability. And so we are interested. So therefore, because remember how we're always interested in the closed loop system. So we're interested in the zeros of f of s. So we are interested if there are any zeros of f of s in the right-hand plane. If so, it is unstable. Remember, we always want it in the left-hand plane to be stable. And so we always look at our closed loop system. So that's why we're looking at the zeros of f of s, since those are actually the poles of the closed loop system. So we're going to look at the right-hand plane. So the contour that we call C of s, that covers that entire right-hand plane, is called the Nyquist contour. So what we see here in our graph is Nyquist contour basically looks something like this, where it has the real part, has the j omega, but it's going to go up to infinity. And then from here from 0 up to infinity. And then it's going to go along here all the way up. This is our Nyquist contour, C of s, and it's going to go down to negative infinity. Our radius here is going to approach 0. So this is our radius r here. R approaches infinity. And now that we have that, basically what we're going to look at is the closed loop system. What we're going to see here, remember, f of s is defined as 1 plus h of s g of s, which is equal to, and remember, isn't h of s g of s just L of s in our open loop system? Basically, the closed loop system is stable. System is stable if all zeros of f of s lie in the left-hand plane of the s-plane. Okay. So now that we know that, what we're going to have to determine is we're going to have to look at when we do this analysis, we often have our f of s, remember, was defined as 1 plus L of s, because it's 1 plus g of s times h of s, which is just L of s. But this makes us, so from this, we determine the number of encirclements, which remember is just capital N of the origin. which is at 0, 0. And so what we do is instead, to make it easier, we define f, and then this is f prime, which is f of s minus 1, which equals L of s, because f of s minus 1 would just equal L of s. And so by shifting the contour C of f, which is the contour in the f of s plane, 1 unit to the left. Okay, so shifting it 1 unit to the left, we're going to count the number of encirclements around -1, 0. So that's 1 shifted over to the left because it's a lot easier to calculate. And so now that we did that, we're going to look at an example where if it is stable, remember, we don't want there to be any zeros in our right-hand plane when we're trying to determine this. And so what we're going to do is we're going to try and determine the stability. So let's look at an example. And so from here, this example we're given in the S plane. So we have a sigma and j omega. We're in the S plane right now. And we have our contour C of S because we're in the S plane. So that makes sense. It's C of S. So I'm going to call this contour C of S. And here's our open loop zeros and open loop poles. And so we have our open loop zeros and poles, and we're going to transfer this over by L of S, because that's what we determined. In order to map, it was easier doing L of S than L of S plus 1, because we use the F prime of S. So when we transfer it over, we get the following contour in the F of S plane. And so here's our -1. The contour looks like the following. Goes in this direction and goes outwards in this direction. So we have to determine, is this system stable? And so N equals Z minus P, where this is going to be, if we're looking at it, how many encirclements do we have about -1? 0. So we have 0 encirclements about -1. Nothing's going around -1 here. It's all encircled. There's a circle around the origin. There's a circle between -1, 0, but nothing around -1. So now what we determined is that, are there any poles that were inside the contour? Open loop unstable poles in the right-hand plane? There were 0, because our contour, remember, is defined all in the right-hand plane here. And so were there any from these open loop poles and zeros? Were there any in the right-hand plane? No. So this is 0. And so Z, therefore, must be 0. So the system is stable. Because remember, we're so interested with these open loop zeros in the right-hand plane. Because remember, the zeros of F of S are poles in the closed loop system, so that would mean it's unstable. So the system is stable right here. Let's look at another example. Okay. Here we got our J omega. And here we have our contour. And the origins right around here. and we have open loop zeros and we have open loop poles. And notice that our encirclements here we have over here. We have the point -1. And this one's going to go over this way. And this one's going to then go over this way. So the number of encirclements we have here in the f of s plane, n is going to be 2. It's circled around -1 once, twice. And then remember, n is equal to z minus p. We only have 2 zeros, but notice that we do not have any poles inside here. So it's going to be 2 is equal to z minus, there's no poles inside, so z equals 2, which we figured because there's 2 in there. So the system is unstable because we have 2 zeros in the right-hand plane for f of s. And because we have 2 zeros in the right-hand plane for f of s, that means that the closed loop system is unstable. So therefore, this is unstable right here when we do our, so because our z is 2, it's unstable. Z must be 0. We need to have 0 zeros in the right-hand plane. So now that we have that, basically, now that we talked about that, we have to look at how do we even graph a contour? That's the biggest thing. That's the hardest thing I think to do, is knowing how to properly graph one of these contours in the C of F plane. And so we're gonna divide it up into 3 segments basically. So sketching the Nyquist diagram. So to sketch the Nyquist diagram, what you have to do is here, remember your contour looks like this, and you have 3 segments within it. The first segment goes from this 0 point up to infinity. The second segment goes from infinity to negative infinity. And third segment goes from negative infinity to 0. So you map basically for segment 1, map segment 1 to find polar plots when omega goes from 0 to infinity. And then your next one for segment 2, you basically go from beta equals pi over 2 to negative pi over 2. It's basically when, let me see, omega equals 0 to infinity. This is when your real part of GJ omega equals 0 to the imaginary part, which is when it would cross the x-axis. So what we're going to see here is you would know when the real part's equal to 0, and then the imaginary part of GJ omega is equal to 0. And then what we look at here is then we see from negative infinity. So this would be 0. If we can determine 0, the point at 0, the point at infinity, and the point from when the real part is 0 to when the imaginary part is 0, then you know it's just the symmetric about here. So then you just graph the opposite to get 3. So map segment 3, that's just using symmetry. And so we're going to see a chart for doing this, which I think makes it a lot easier. Okay, so for this system, we're going to see that we have a uni-feedback system. So for this example, we're going to have an input R best. Then it's going to pass through where we have a plus and a minus here. Summing junction, unity feedback, they just said E of S for the error, but that doesn't matter here. We have our G of S, and then it goes through, and it's going to go through to C of S. So they gave us that G of S is equal to 1 over S plus 2, and they said find the Nyquist diagram. So here, remember, for a Nyquist diagram, we're going to have 3 specific segments. So let's start from the first segment. That first segment, we know it's basically from our G of S, we know we have a pole at -2. Okay. And so when I'm looking at this, I'm going to make a chart. And so my omega, my real part of J omega, and then my imaginary part of J omega. And this is going to help me in order to sketch the diagram of our Nyquist plot. So for when my omega, it starts out at 0 here, because we're going to see when it's equal to 0. The real part here, we're going to get when 1 over 0 plus 2, because this is just J. If you translate this over, J omega is equal to 1 over J omega plus 2. 1 over 0 plus 2 would just be 1/2. And then the imaginary part, we would see that there would be no imaginary part here. It would just cancel out to 0. And then for other one, if you want to see the imaginary part specifically, how that comes into play, if you did J omega minus 2, J omega minus 2, you're going to get -2 plus J omega all over. And then you're going to get omega squared, so minus omega squared, and then -4. Then if you split this up into the real and the imaginary part, you're going to get 2 over omega squared plus 4. Then you're going to get minus J omega all over omega squared plus 4. So that's how you split it up in real and imaginary part. So this is the real part right here. So this is the real part of J omega, and then this is the imaginary part of J omega. And so if you look specifically at, well, what is the real and what's the imaginary part? Real part, if you plug in 0, you get 2 over 4, which is 1/2. You plug in 0, you get 0 over 4, which is just 0. Then when we look at when omega goes up to infinity here, when omega goes up to infinity, you're going to see that's 2 over infinity, which is 0. But here we're going to get infinity over infinity squared. If you do L'Hopital's rule, you're going to just get over infinity, you'll get 0. And so for the first one, we're going to see when you go from 0 to infinity, basically on our plot, what it's going to look like is when we're at omega 0, we have 1/2 0. So at the point 1/2 comma 0. So for a real part of J omega versus our imaginary part of J omega, we're going to see at 1/2 0, where when omega goes to infinity, it's going to be at 0 0. So when we transverse across this upwards from 0 to infinity, we're going to notice that it's going to go from 1/2 to 1/2 comma 0 to 0 0. And so that's our first segment. Our next segment is going to be going from that positive infinity downwards to negative infinity. And so if you plug in values, what you're going to see as you plug in specific values, you're going to get, because you'll determine specifically the angle as you increase it. You can determine the angle from this one. So remember, your J omega is equal to, and then you have, because this was finding the real imaginary, you're going to get 1 over J omega plus 2, and then you're going to get for your J omega, knowing your specific angle is going to be minus tan inverse of omega over 2. As you increase omega, notice here, when omega equals 1, it's going to be minus tan inverse of 1 over 2. Minus tan inverse 1 divided by 2, which you're going to get -26. And so that's why we were seeing here, it started to go more this way from our 0 degrees, as it kept increasing, like 100 divided by 2, we're seeing that it's getting closer and closer to -90 when it approaches. So as omega goes to infinity, it approaches at -90 degrees here at that point. So that's why we say from 0 infinity, it was approaching from -90. So that's why we came in at this angle. And then now that we had that, we're going to see that our next one, basically, the exact opposite is replicated from this one right here. From segment 3, for sure, it is going to be exactly the opposite. So this would be due to segment 3. And then at segment 2, we're going to notice from positive infinity to negative infinity, basically, it will remain the same. We don't have much difference here as in the other examples. If you do the calculation here, if you do negative infinity, it's just 0, 0. It doesn't change any points. So even if you plug in from positive infinity to negative infinity, it's still 0, 0. Nothing changes. You remain here at segment 2. But segment 3 is the opposite because it's the symmetrical. So that's what you're going to see there. Now that we talked about, we need to look at specifically one example where we're going to go from, let's see, 0, infinity. I think this one, I believe, is pretty good in terms of understanding where this sort of takes place for this example, for the stability of a closed loop system, because I think it relies a lot on what you have to know. And so I think this one's more what he wants us to see if we were given one of these questions. When g of s is equal to 500 all over s plus 1 times s plus 3 times s plus 10. Okay. And so for this, we have to determine the contour into the f of s plane. So here we have j omega, and then here we have our sigma value. And so our pole is at -1, then -3, and then -10. And so here, those are our 3 poles. And what we have to do is we're going to have to determine the contour. So the first step, remember, is we go from 0 to infinity. And so we're going to have, you'll notice in our chart, it's going to be a little different because there's actually more happening within this plot. So first, if we start at 0, we need to look at the real part of gj omega. Then we're going to have to look at the imaginary part of gj omega as well. And so from this, what we're going to see is if we replace this, so we just get a gj omega, it's going to be 500 all over j omega plus 1, j omega plus 3, and then j omega plus 10. Okay, now that we got that, you multiply by the conjugate to get the j out of the denominator. So if you multiply this entire thing by the conjugate, you're going to get 500 times j omega minus 1, j omega minus 3, j omega minus 10. Okay, now that you do that, what you're going to see in the denominator happen is multiplying this one by j omega minus 1, you're going to get minus omega squared, and then you're going to get a minus 1, and then you're going to get a minus omega squared minus, and then 9. Then you're going to get a minus omega squared, then you're going to get minus 100. Okay. Now that we have that, what we're going to do is with this, we need to separate it. So we need to multiply it out in the numerator in order to get the j terms all together, in order to separate the real part from the imaginary part. And so in order to separate the real part from the imaginary part, we're going to get j omega is equal to, so this would be multiplying, I get 500 times j squared negative omega squared. And that's going to be minus 3j omega minus 4j omega is j 4 omega. Then we're going to get plus 3 times j omega minus 10. And then all over here, we're going to get, if we have this factored out, basically, we're going to get an omega to the 4th, and then we're going to get plus 9 omega squared plus, okay, so then plus 10 omega squared. Then we're going to get a plus 9 times 100 minus, or wait, no, that'd be still negative omega squared minus 100. So then multiplying the numerator out again, getting this one multiplied by this one, we're going to get, let's see, it would become j omega, so that'd be 500, then minus j omega cubed. Then we're going to get minus j squared, which would be plus, and then that'd be 4 omega squared. Then we're going to get plus j3 omega. Yes, and then we're going to get plus 10 omega squared plus j40 omega plus minus 30. Okay. And then in our denominator here, what we're going to have is we're going to get an omega to the power of, we can leave the denominator like it is because we're just going to plug in omega, so it won't matter. There's no j terms in it. So plus 9, then minus omega squared minus 100. Okay, then now when we simplify the j terms, we're going to get 500, and then it's going to be times, and then gain the ones that don't have j terms. We have 14 omega squared. Then we're going to have minus 30. And then for imaginary part, we're going to have minus j, and then it's going to be omega cubed, and then 3 omega plus 43 omega all over. And then it's going to be omega to the power of 4 plus 10 omega squared plus 9, and then minus omega squared minus 100. Okay, so now that we got that and we're able to break it down, this is the real part right here. This is the imaginary part. What we're able to do is once you fill this out, you're going to notice when omega equals 0, your imaginary part is just going to be, sorry, your imaginary part will be 0, of course, because the numerator will be 0. And what you're going to see for your real part is it's going to come out to, when you do all the calculations, it should be 500 over 3. And then when you plug in to get your real part equal 0 and your imaginary part equal to 0, these are really big. The 4 values that you test in here is when your omega 0, when it's infinity, when your real part is 0, when your imaginary part 0. And so when you test all these values into your equation, because this is the real part right here, and this is the imaginary part connected to the j term, you're going to get 1.4639, then here it's negative 8.3597, then 6.5594, negative 0.874100. So testing when omega 0, because when it's 0, then when it goes to infinity, then you're going to test when the real part is 0. So at that point, when the imaginary part 0 at this point, then you do the symmetry in order to get the rest of the graph. And so that's why those are so important, those points. Pretty much then, once you plot it onto the plane, you're going to notice that from these, when you go here, you're going to see that your contour will end up looking like, let me see if I can fit it here. So we're going to have intersection points where this would be our, when omega is 0, this would be our 50 over 3. 50 over 3. So this would be the point right here where we have the first segment when we start at 0. And when we're going up, in order to reach our point, which is at when our real measuring negative 0.8. This would be once we hit then this point when the imaginary part, when we see when our imaginary is 0, it's actually going to go here because we're going to see that we're going to hit that negative 0.8741, and then we're going to go and then we're going to hit when both of them are 0. So we first go from 0, then it's going to hit this one intersection point. So it's going to hit that intersection, then it's going with the imaginary axis when it's equal 0 at negative 0.8741. Then we're going to go up and we're going to run into when omega is infinity, it goes to 0, 0. And then now from that point, everything is just the opposite reciprocal. So we're going to see here when we do our opposite reciprocal, it's going to look like the following. It's going to just be the opposite of the beginning wave. And so that's how we get this plot here. So the Knightwitz diagram in summary of how we got that plot. And then at the very end, he talked about gain margin and phase margin. And to conclude on those two topics, basically the phase margin versus the gain margin is the gain margin is known as gain margin is going to be described as the amount of K added to system before the system becomes unstable. And the phase margin is going to be the amount of phase added to system before the system becomes unstable. And so looking at a quick example before we tonight, when we have and they basically have our real and our imaginary part on them, we notice that when we have it here, our real versus our imaginary, we're going to notice that if we want to increase the gain, it would make the curves look like this. But they'll never intercept the point -1. And so what we're going to notice is that the gain can equal infinity because it never intercepts the point -1. But our phase margin, the phase margin would be if you start to tilt this upwards. If we start to tilt this upward, it's going to run into -1. So the phase margin, so the gain margin is infinity. So I just write gain margin because you can add as much gain as you want, but it's never going to go through -1. But the phase margin is going to be small. Because if you tilt it upwards, it's going to run into that -1 point. And then looking at another one, let's look at another example where we're trying to get an understanding behind this, is where we have -1 here, and we have a gain margin. Well, if we have our gain here, basically, once we get for a gain, if we keep increasing, so sorry, let me put this in black. If we keep increasing the gain here, you're going to notice that it's eventually going to pass through in that -1 point. So our gain margin here, if we keep increasing, we're going to pass through. So at that -20 log, and then it's going to be the L of J where omega is 180 degrees. He didn't specify too much on that, but that's where it will intercept at. And then the phase margin, we're going to notice when you tilt this, it is going to intercept, specifically if this point was at negative j, let's say, but none of the other points were at -1, so it's more like a circle, it would then intercept at -1 here if you tilt it by 90 degrees. So the phase margin would equal 90 degrees. Okay, that's pretty much it, and that's where I want to leave it all on the night quiz. It's a little more of a complex subject, I feel, but that's where I'll end it. So let me stop the recording real quick.